Hey guys, welcome to today's lesson. Today we're looking at applications to calculus, looking at the minimum and maximum, often just denoted by min and max. Okay, before I do that, I'm just going to, recount on what we've already learned with turning points and stationary points and those types of things. So first of all, we've learned that for a stat point, stat point or a stationary point, we always look for dy dx is equal to 0. Of course, that's because we have a gradient function, and we know if we're looking for a turning point, let's say a turning point below there, the minimum one, we know that it has a gradient of 0. We have the maximum point up here, we have a gradient of 0. So we let dy dx equal 0, and then we so differentiate the original equation, and then we solve it for 0. Once we've got that, we then determine the nature of that turning point. And we do that by looking at d squared dy dx squared, or y double dash, and we look to see if it's greater than 0. We then know it's a concave up, which means we have a minimum turning point. If we find out that d squared dy dx squared is less than 0, then it's concave down, which of course means that we have a maximum. And obviously you can start to see when we have minimum maximum questions why this is quite important. Of course, though, when we're looking at these stuff, we do have some cases where d squared dy dx squared, or y double dash, is equal to 0, in which case we have a possible point of inflection, and then we need to test left and right of those signs. For we have our x and our y double dash, we usually put the x value that goes inside of here, and then we usually go let's say x take away 1, and then we take x plus 1, and we want to look at here if it's going to be a change, for example a negative and a positive, or a positive and negative, which means of course we have a concave down for the negative, and then concave up for the positive value there. So that then proves our point of inflection. So look, we've got two main things that we kind of do here to determine natures and stationary points and those type of things. So what is this lesson about? Well, we've got an application to calculus. I'm just going to start with one question to kind of walk you through this. So in a maximum minimum question, it will generally have the word a maximum or minimum. Apologies. You can see inside here we've got that word minimum. So a farmer wants to make a rectangular paddock with an area of 4,000 meters. There are a couple little points I'm going to have here. The first of all, it's good to have a diagram. Good to have a diagram. So for example, in this question, it talks about a rectangular paddock, so I'm going to draw up a rectangular paddock. It doesn't give me any lengths, so I'm going to say we've got lengths of x and y. But it does say that we've got an area of 4,000, therefore x times y is equal to 4,000. And what you'll find is that you're looking at forming an equation. I'm going to say forming a differential equation, and then a point you may need to link. You may need to link two equations, because what it says after that is that it says, however, fencing costs are high, and she wants to she wants the paddock to have a minimum perimeter. So what I mean by a differential equation, it's an equation that we're going to differentiate. Now, in this case, the differential equation is about the perimeter, right? What we've currently got is a formula for the area, because we know the area equals 4,000. So occasionally, and I think this is actually more often than not, you may need to link two different equations. For example, if I look at perimeter, right, and this is something that I have to form because I want to differentiate to find the minimum value of this, we're going to have 2x plus 2y. Of course, that's because we have a perimeter of x plus y plus y. Okay, we don't know what those lengths are going to be. And of course, I cannot differentiate this equation because I've got two variables, two unknowns. We know that, on the right hand side I should say, so we actually have three unknowns altogether, which we can't have. We need to have a subject, and we need to have a one letter in there, a one variable equation. So what I'm going to do, I'm going to use this other information that they gave me in the first part of the question. Now, note that they actually give you the differential equation here. So I already know that I don't want to have any y's in there. So what I'm going to do is I'm going to rearrange this to make it y equals 4,000 divided by x. And now what I'm going to do is I'm going to substitute into that differential, or into that equation, sorry. So two lots of 4,000 over x. And now I'm going to simplify by multiplying that out. 2 times 4,000 is 8,000. And then I'm going to look back and say, hey, I have solved that equation. Or not solved it, but I've created or formed that equation as required. Okay, as required. So that's the first part of this question, and there are three parts, and so obviously that's the first one, and that's quite a common question. Now, of course, the good thing is if you can't get to that equation, you can certainly use the equation in the second part because they're provided. And HSC, guys, that's usually the hardest part, I feel, because the second part of that, okay, well, let's call it number 3, we want to solve the max or minimum using calculus. And this is what I was just going through previously. So we know for a stationary point, because we want a minimum point or a maximum point, in this case we want a minimum, we need to show first of all what the stationary point is, where that minimum max occurs, and then we want to show that it's minimum. So what I've got, I want to show dp dx, okay, that's going to be my differential equation. We've got 2 plus, now of course we don't like it in this form, so I'm going to rewrite this, p equals 2x plus 8,000 x negative 1, okay, so now I can put my negative 8,000 x to the negative 2. Of course, if you recognize straight away that you can rewrite that to be 8,000 over x squared, that's probably a quicker method of doing it, I guess, and that's my differential equation. So we've got my equation, and then we've got my differential equation. Now, I just want to make sure that when I say form a differential equation, it's not probably very accurate. I want to form an equation that I am going to differentiate, okay? Once I've got that, we know that we're going to let, oops, not how I spell let, we're going to let p dash equals 0 for minimum maximum value, or for stationary point, or whatever you want to have. Okay, therefore we've got 2 minus 8,000 over x squared equals 0. We've got 8,000 over x squared is equal to 2, so I plus that across, so I got 2x squared, and divide by 2x squared equals 4,000. Therefore x equals, so I'm going to square root 4,000. It does say in here to 1 decimal place, so we're going to do it to 63.2. It's a very good idea to write the whole screen out in your calculator just to make sure you don't get that rounding error. And I'm also going to put here, because x is greater than 0, because think, if you square root that, you do have a positive and a negative 63.2, but of course you can't have a negative distance. Okay, so that's the second part of that question. I've found my x value. Now I'm just going to double check that, and it says find the dimensions of the rectangle. Okay, well I haven't found the dimensions, I've found the x coordinate. So I'm going to go back up into my original equation, y equals 4,000 over x, and I'm going to chuck that in to find my y coordinate, and it happens to be y is also equal to 63.2, which means that my rectangle is actually a square, and what you'll find, that will be very common. Okay, my last situation, okay, my last part of my question, I'm struggling for room here. It says calculate the cost of the fencing. Okay, well I've got 4 times 63.2 ... I'm going to use whatever's in my calculator. I'm going to times that by $48.75 per meter, and if I throw all of that back in, okay, if I throw all of that back in, then I'm going to get approximately, I'm going to use my little approximately symbols, we've got $12,000 or $12,332.88. Okay, so that's basically what your application question for minimum maximum can look like. Again, first of all, if you can draw a diagram, draw a diagram. Second of all, form an equation that you can differentiate, and of course you may need to link, and most likely you will, 2 different equations together. And then third of all, solve the minimum maximum problem via calculus. So find your dy dx, let it equal 0, find your point, then d squared dy dx squared to prove concavity minimum maximum. Okay, and then go through from there. Now, just one thing I noticed here, I didn't actually prove my minimum maximum. That's a bit of a problem, because I would certainly lose marks for that. Okay, and I guess I'm kind of out of room here, so it makes it a little bit difficult. If I was doing that, okay, of course my p double dash would be equal, and I'm going to use from this one here. So the 2 disappears. Negative 2 times negative 8,000 is positive 16,000, and then x negative 3. Okay, of course we're using 63.2, so when x equals 63.2, p double dash, I'm going to throw that back in. Okay, and that's going to be greater than 0, which means it's concave up, which means you can see there it's a minimum point. Okay, really important, guys, that you do need to show that, and most likely I would have lost marks had I not have shown that. Okay, I'm going to show you another question, and apologies, there's a lot of stuff being written up here, so I do apologize, but you can see that these questions aren't small by any means. Okay, so we've got the next one. You might want to pause this and have a crack at the question, but otherwise we'll jump straight into it. So we've got a box that's made up of 80 centimeters by 30 centimeters. Now look, we've got a diagram here. For my purpose, I don't want to rewrite it, only because I'm struggling with room. We've got a cardboard here, rectangle by 30 by 80, and we're taking 4 equal squares out of size x. So those little sides are x there, which means that if I look at this actual box here, that length there, I always do that, that length there is going to be 80 subtract. Now if that's x and that's x, we're going to subtract 2x. If I want this length inside here, now remembering that's just the bit in red, okay, and this little bit would be 30 minus 2x, because I'm taking the x there and the x there. Now, it does say that we're folding up the corners to make an open box. So what I might do, I might just draw this underneath. Again, I'm just trying to save a little bit of room here. I'd make these diagrams really nice and big. Okay, we've got our lengths there, as we've just seen, are going to be, the base would be 80, take away 2x, okay, and the breadth there would be 30, take away 2x. And of course the height would be the height of those little squares, which would be x. Okay, so let's look at part A. Show the volume of the box is given by this equation. Okay, so in this case, we want to form an equation for the volume. Okay, I'm not really giving any other information. I'm not giving surface area, I'm not giving area, etc. So I'm going to jump straight into the volume of a rectangular prism, or a cuboid if you're on the other side of the world. We know that we do that by saying, in this case, the base times the height of that little rectangle. Okay, so 80 take away 2x times by the height of x, and then I'm going to times that, of course, by the depth of 30 subtract 2x. Okay, so it's a fairly long equation there. Noticing too, this is going to be a nice one because I don't have to link anything else in because I've just got x's there. So 80 times x is 80x, take away 2x squared, and of course put that back in brackets because I'm going to be timesing that by 30 take away 2x. And be careful because there are lots of places where you can make silly little errors. 80x times 30 is 240x, then 80x times 2x is going to be negative 160x squared, minus 2x squared times 30 is minus 60x squared, and then plus 4x cubed. Now I'm going to go look back at my little equation there that they gave us. So we've got 4x cubed, which is that part there, so that works out really nicely. We've got 220x squared in the middle, so minus 160 minus 60 is minus 220x squared. All right, so far so good. We've got this plus 240x at the front there, and I've made a little mistake, haven't I? Because it's not 240, it should be 2,400. And luckily, as I said, there's lots of little areas where you can make mistakes, and that's a really a good thing that I've done there, so it can show you how easy it is just to make a silly little error because I'm trying to rush. Okay, but I've got that there, and that's the benefit of having the equation given to you. You can see what it is, so you can try and form it. Okay, so I've got my equation that I'm going to be able to differentiate. Part B says find the value of the x that gives the box its greatest volume. So it doesn't say maximum, minimum, but of course, okay, that means the biggest, the greatest. So we're looking at, I'm going to use v dash. Usually v dx is probably a little bit nicer. Okay, 3 times 4 is 12x squared, minus 2 times 220 is 440x, plus 2400. Okay, so I've differentiated. Now we know we're going to let dv dx, or v dash equals 0 for the minimum and maximum, or for your stationary points. Therefore, we've got 12x squared minus 440x plus 2400 equals 0. Now that's quite a big one. And you could go and through and factorize this, but to be honest, we just want to solve it, right? So because they're big factors, 12 doesn't go to 440, so it's probably going to be 4, and it's going to be a non-monic binomial. Yeah, it's going to be a bit funky. So what I'm going to do straight away is I'm just going to use the quadratic formula. It's one of the reasons why we learned it. So x equals negative b. Okay, so negative 440. X equals negative b plus or minus the square root of b squared minus 4 times a times c, okay, all over 2a, which is 2 times 12. Okay, now I'm trying to save room here, but generally speaking, you're going to go through and you're going to whack that all into the calculator. So make sure we do the plus 1 first and then the minus 1. We get x equals 30, and we get x equals 20 on 3. Now, sometimes what will happen is, you saw that last question, you might get a negative, and then you can discount the response straight away. This is a problem. They're both positive. They're both possible. But why I like this is it really does force you to make sure you don't forget about the double second derivative, okay, double dash, or dv squared dx squared, because if I do my v double dash, in this case v double dash will be 2 12s to 24x minus 440. We can test each point, x equals 30, v double dash, I think that's going to be greater than 0, which means that's a minimum, which means my x equals 20 on 3. If I put that into my v double dash is less than 0, which is negative, which means I've got my maximum. Therefore, I can state, therefore, x equals 20 on 3 for the maximum value. Okay, so that's a fair amount so far. I'll go back, and it hasn't actually said find x. It says find the value. Oh no, it does say find the value of x that gives the greatest volume. And the last part of my question, and this is always important, read to make sure that they just don't want x, because often they want the actual volume. So find the maximum volume. I'm simply going to go back to that original equation there, and I substitute the 20 over 3 for the x's. I'm not going to do it visually, only because I don't have enough room, but if I do that and I throw it all back in, okay, we're going to get something like, so I'm just going to do it with my calculator, 7,407. Now it doesn't say anything, so I'm just going to whack in a couple of decimal points there. Maximum volume, so that was in centimeters, so centimeters cubed. Okay, so there we go. We have a nice maximum minimum problem. Look, that's 21 minutes long. It's enough. If you want me to do some harder questions, I can. But look, again, those steps that you need to ensure. Okay, so number one, we want to draw a diagram if possible. Number two, we want to form an equation for differentiation. Okay, remember, you may need to use two equations to do that. If you're trying to figure out which equation you need to differentiate, look to see what they're looking for in terms of, you know, if it's a maximum time, then you want t equals. If you want a minimum, what was it in the last one, like the width, okay, then you want x equals. Okay, so it's whatever that they're looking at, and often they've already given you the equation, so you just need to look and see what you need, and then you can, that's the equation you want to have. Do I need another one to help me get it? Okay, what are the information they're giving me? Then we're looking for use calculus for the minimum and maximum. Don't forget though to determine the nature. Y double dash, that was Y dash, and then 4, of course, answer the question. All right, you've done all the hard work, put it all together to finish the question off. All right, guys, that's our minimum and maximum application to calculus. Sorry for the length of the video, but certainly know that takes some time. Any questions, please ask me in class, or certainly drop me an email. Have an awesome day.